In previous 3 talks in this session, we heard great things about provenance and audit logs and how they are useful in attack investigation. But you know what? Those folks did not tell you the limitation of those audit logs that can basically lead to inaccurate results during the attack investigation. But worry no more, because we are going to solve or tackle those challenges in this talk through the unification of logs from different system layers. So over the last decade, the data breaches have gotten out of hand. And in 2008, there were more than 600 reported data breaches, which leaked more than 35 million records. By 2018, the number of breaches doubled, and the number of records exposed increased by 10 times. Despite such a rise in the data breaches, the security analysts or administrators still don't have right tools to investigate those attacks or alerts in a timely manner. According to a survey by RSA in 2016, 73% of cyber analysts have inadequate level of skills to respond or detect attacks. So one of the ways to actually detect attacks or threats is to use audit logs. Audit logs are basically maintains a history of system execution. These are system-level audit logs are usually collected by intercepting system calls. For example, if a user starts a Firefox process, and this Firefox process downloads a PDF file, and afterwards this Firefox process downloads a mal.exe file, then the system log of this whole execution is shown on the slide. So these system logs are usually parsed into a graph structure called data provenance graph. In this graph, the vertices represent file objects, system objects like file, processes, or sockets, while the edges between these vertices represent causal dependencies. Investigator or administrators can use this graph to find the root cause or the ramification of the attack using a backward tracing or forward tracing query, respectively. For example, if you see a mal.exe process was sending a suspicious connection to a socket, then you can use this graph to find out how this mal.exe was basically downloaded into your system. Now let's consider a very simple attack on a WordPress website. Requests to this website are first load balanced using an HA proxy. Afterwards, these logs basically, these requests goes to Apache web server, and then the user records or transactions are recorded into a SQL database. In addition to system-level logs, these applications were also logging their inherent logging application logs, application events. Now consider an attacker which performed a simple SQL injection attack to steal the credentials, and then which led to basically also the website defacement. Now the investigation, after the detection, the admin can proceed for the investigation. In this case, the admin knows that the account's data table was basically accessed by the attacker. So the admin grep this account table on the PostgreSQL query logs. And the return and the grep query will return a query which will indicate that this was essentially a SQL injection attack. Now, now the admin cannot proceed further in the investigation, even though the admin knows that the HA proxy logs or Apache logs have some evidence related to this attack. But because these application logs do not capture the workflow dependencies between these applications, it's not possible to associate which log event is related to the SQL query that led to SQL injection. And to further find or proceed the investigation, that the admin will now use system logs, because system logs basically allows you to track or trace the dependency across applications. In this case, the admin knows that this database file was accessed when the query was executed. So the admin will issue a backward tracing query from this file read event, which will return you a provenance graph. And once this provenance graph is returned to the administrator, it will lead to a dependency explosion problem. What this problem is basically based on an assumption that an output event depends on all the preceding event that happened before. And even though we know that there is only one request that led to the SQL injection, but you cannot find out from this provenance graph because of these false dependencies. Moreover, this provenance graph does not provide you with any sort of application layer events that we saw earlier. So to reiterate, the provenance graph that I showed you before suffer from two challenges. The first one is the dependency explosion problem, and the second one is the semantic gap. So to solve these challenges, we built a system called OmegaLOG. It solved the dependency explosion problem by identifying the event handling loop inside the application using application event log sequences, such that each iteration of the event handling loop is considered as one semantically independent execution unit. This definition is same from the beep system that was introduced in NDSS 2013. But unlike beep, we don't require any sort of instrumentation or training overhead. To tackle the semantic gap problem, we will graft the application logs event onto the system-level provenance graph in a causally correct manner. But before we build the OmegaLOG, we asked ourselves a question that how many applications usually log something inside their event handling loop. So we took 79 Linux applications, and we looked into their man pages or source code to find out are they logging inside their event handling loop. We found out that the 64 of these applications were either logging at info level or debug level, or at both of these levels, while there were 15 applications which weren't logging anything. And these 15 applications were either lightweight applications which were designed to keep the resources low, so they don't log anything. And the second category was the GUI application, where even though there was an event handling loop, the event handling loop did not match the expectations of the forensic investigation. So once we have even enough evidence that application basically logs inside the event handling loop, we built OmegaLOG. So the OmegaLOG consists of 3 different phases. The first one is the static binary analysis phase. The next one is the runtime phase, and the final phase is the investigation phase. So to start with static binary analysis phase, we will first identify the log printing functions inside the binary. This is because we want to separate that which are the normal file writing functions and which are basically the log file writing functions. So for that, we use certain heuristics like functions from well-known libraries like log4c, or functions that basically write to var log directory. Once we have identified these log message printing functions in the binary, we will move to a static analysis phase where we find the call sites to these functions. And then we try to concretize these log messages which were passed as to the arguments to these functions. Once we have find or concretized these log messages, we will build a regex from these messages so that we can match these log messages with the runtime application events during the investigation phase. Finally, we perform a control flow analysis on this binary so that we have all the valid log message control flow paths that can occur during the execution of the program. For example, for the code snippet that is shown on your left will generate the control flow paths shown on your right. Note that these control flow paths essentially allow us first to identify which one is the event handling loop, and then allow us to partition the application into execution units. So now after this offline phase, we move on to the runtime phase where we collect both the application logs and the system level logs. To collect application logs, we use Linux audit module. To collect the application logs, we build a custom Linux kernel module, which basically intercept every write syscall. The idea here is that we want to capture every application event because we want to add PIDs and timestamp to these log messages so that we can find out where we want to graft them or encode them into the system-level log entry. Finally, we unify these system logs and runtime log messages into a single log, which we call it universal provenance log. Now let's say if an attack is detected or a symptom is detected, investigator can use ωLOG. For that, they will use the control flow paths that we built before and the universal provenance log. And our log parser will partition the log into the execution partitioned units, and then it will generate an execution partition graph. Once the execution partition graph is generated, we will add the log messages from the universal provenance log onto this execution partition graph. In the end, we will have a graph which is both the semantic aware and execution partition, which we call it universal provenance graph. Now, back to the case study that I mentioned in this presentation. We recall that we have two logs. So we had the application logs, and then we have the system log, which we parse into the provenance graph. Now we use ωLOG on this thing to combine, to solve the challenges of the provenance graph, and it will basically generate a universal provenance graph. And from this graph, we can see that which SQL query actually led to the SQL injection attack. Moreover, we can see the one request that led to this attack. Not only that, we can also reason about why the website was defaced. In this case, we will issue a forward tracing graph from that request that we identified in the previous graph to find out that the WordPress file plugin was used to write to index.html, which led to website defacement. To evaluate our system, we took 18 different applications from different software categories with different sizes. These applications, out of these 18 applications, 16 applications were either logging at info or debug, or at both of these levels, while 2 weren't logging anything. We first measured the static analysis time, which was basically, which had 2 parts. The first part is when we want to concretize the log message string, and the next part was to generate the control flow path from these log message strings. We found that it took around 12 seconds to 1 hour to first concretize the log message string in the binary, and it took around 1 second to 4 minutes to generate the control flow paths from those log message string during the binary analysis. Note that this is just a one-time effort to basically generate these control flow paths, because as long as the binary itself doesn't change. We also measured the coverage of our static analysis, where the coverage is basically defined as a ratio between the concretized log messages that we were able to get and to the ratio of the identified call sites of these log printing functions in the binary. We found that all these applications have more than 95% of the coverage, except for the 4 applications. Finally, we also measured the runtime overhead, because we were intercepting every write syscall on this system. We found that our average runtime overhead was around 4%. Some of the applications, such as Memcache or ProFTBD, had a higher runtime overhead because these were write-intensive applications. And since we are intercepting every write syscall, we were supposed to get this kind of runtime overhead for these applications. OmegaLOG does suffer from certain limitations. The first one being is that we need at least 1 log message inside the event handling loop so that we can partition the loop. But we envision that good logging practices will solve this limitation. We also only work on C, C++ binary. This is because of our implementation detail, where we use Anger binary analysis tool. The third one is basically we do not cater the program that use synchronous I/O programming model because they don't print the log messages in a sequential order. So to conclude, we proposed a new execution partition technique that does not require any instrumentation or training. We were able to encode semantic information onto these provenance graphs using application log events. We used a program analysis technique to reconcile these application log events onto the provenance graph. And our evaluation showed that we achieved low overhead, and we were able to perform high-fidelity attack investigation. This concludes my talk, and I'm happy to take any questions now.
Kangukji from the University of Texas, Dallas, and thanks a lot. This was a great talk. So yes, I think overall your approach makes sense, but my more question is about maybe related to your future work. So I want to ask you about what is your idea to expand your work to cover a different programming model, as you mentioned, asynchronous event-driven like programming. Is there any way that you think we can tackle the problem, or that this is just difficult problem cannot be solved?
So the one reason what we want is that we want to build an instrumentation-free environment. And in that case, the reason these asynchronous applications were printing logs out of order, so it was hard to actually identify that two applications, if the application is running and two requests comes at the same time, which application log event relate to which event handling loop. So I don't think so there is any way that you can do without instrumenting the application itself, because you need to know that either it was the first loop iteration or the second loop iteration. And that requires instrumentation at the end of the day. Yep.
So while the audience is thinking of further questions, let me ask one. So in your performance evaluation, you said that there were two benchmarks that had slightly higher overhead than the others because they were write-heavy. I noticed that many of the programs you had in that evaluations, I can make arbitrarily write-heavy as I want. Like SSH, for example, was in there. I can make SSH be as write-heavy as ever I want.
Right.
So how did you test those?
So during the evaluation, we use the stress testing benchmark, stress tests. So basically, they were already doing a lot of they were write-intensive application already. For example, in the case of Memcache, we used their own benchmark tool, which was supposed to be stress testing your system. So it's just the case with the ProFTBD and the PostgreSQL where we saw that there was a higher write rate, higher overhead. But yeah, that's correct. That this is supposed to happen because we are capturing write syscall, and there is no way around that one. Yep.
Okay. If there are no further questions, let's thank the speaker one more time, and then let's go for coffee.